Hello everyone. Good evening students. Welcome back to our channel. In the last class we discussed what elasticity is, and we discussed with few examples, and we discussed some of the definitions related to elasticity. I request you all please go through that, revise it and come and watch this session. Okay, so let's recall it what elasticity was that we discussed. If we considered any object, for example a cushion, when we applied some force on it, it got deformed, and then when we remove this deforming force, it will regain its shape by the property of elasticity. We discussed this part. Then we discussed when we apply, suppose this rod we had considered, when we apply some weight on this rod, that means deforming force on it, then some restoring force is produced inside the body because of elasticity, and if this is the area of cross section, this force will be acting throughout this area of cross section, and if we divide this restoring force by area of cross section, then it is called stress. We discussed this part, and we discussed that here this force that we had applied, it was deforming force. We saw that because of this deforming force, the length increases. Suppose it increases by delta L in equilibrium. What you'll see is, after some time when the equilibrium is reached, the downward force, that is deforming force, is completely balanced by the restoring force. Okay, and equilibrium is maintained. They are equal and opposite. Okay, so when we measure stress, we can even measure it in terms of the deforming force by area, because this deforming force is equal to the restoring force. Okay, even if we go on increasing the deforming force, suppose we have increased it by 1 kc, again the elongation will increase, and after some time we will see that equilibrium is reached. Okay, then after equilibrium, length will no longer increase. That means when deforming force is increased in the downward direction, restoring force will also increase, and it will become equal and opposite to the deforming force. We discussed the stress. Then we discussed strain. Strain is the change in length by original length, change in dimension of the body by original dimension. This was longitudinal strain. We discussed 3 types of strain. First was longitudinal strain, then that is change in length by original length. Then we discussed volumetric strain, that is change in volume by original volume. Then we discussed shear strain. And what was shear strain? Here the force applied, it didn't change the length, it didn't change the area, it didn't change the volume, but it changed the shape of that object. For that we had considered a simple example of eraser, in which its lower face was fixed, and we applied force tangentially on this face, on the surface of the eraser, because of which it got turned. This face, which was perpendicular to the fixed face, it got turned by some angle. That angle, if we represent it by theta, it is called shear strain. Okay, now let's try to write its expression of shear strain. Here suppose the length of this perpendicular face, which is perpendicular to this fixed face, is L, and it got turned by the angle theta, and because of which this length by which it got moved. Suppose this length is delta L, then what is theta? If theta is displacement, then it is what? Arc by radius. Theta is arc by radius. So arc here is delta L by, and here radius is L. This is one way by which we can understand this expression of theta. Or we can understand this expression of theta by another way. This theta is small. The angle by which it is turned is very small. So we can write this theta to be nearly equal to tan theta. Okay. And what is tan theta? Turn permanently black. That means it is equals to perpendicular by base. So here what is perpendicular? Perpendicular is delta L, and what is base here? L. This length is L. So this is the expression of shear strain. Okay, till here we discussed. I hope you all remember that. Now let's move to the next slide. Let's start today's class. That is Hooke's law. We have to start from Hooke's law. Okay, before we move into this law, let's recall one example. Let's consider one rod. Okay, we apply some load on it. Suppose we apply the load of 1 kg. Because of this load, its length increases. Extension is delta L1, suppose. Okay, so we are applying load in the downward direction, because of which there is extension in the body. There is extension in the body. Okay, now again if we increase the load, suppose we increase it by 1 kg. So total load is now 2 kg. Then what we will see is its length increases, and now suppose the length has increased by delta L2, so that the total extension is delta L1 plus delta L2. So what we see here is when load is increased, extension also increases. That means if we increase load more and more extension will be produced in the body. That means when we apply load, there is extension. That means extension is the result. That means extension produced, it is directly proportional to the load. Okay, this was given by Hooke's law. Okay, he said that extension produced in the body is directly proportional to the load applied. Later on, his law was modified by Young, and the new law was given as, the statement was given as, within the elastic limit, stress is directly proportional to strain. Let's try to understand this statement. Okay, now let's erase this one first. The statement starts with, within the elastic limit, the stress is directly proportional to the strain. Now, what is elastic limit? Let's try to understand it. Okay, we'll take the same example of the rod, and we'll apply, when we apply the load on the object, then it will get elongated, and when we remove this force, what we will see is it will regain its original size and length, because of which property? That is elasticity. And because of elasticity, why? Because restoring force is acting in the body, because of which it tries to regain its original length. Now we will keep on increasing the load. Suppose we have applied the load of 9 kg, and again we remove the load. We will see that after some time it will regain its original length. Now let's increase the load. Okay, we increase the load by 1 kg. Initially there was 9 kg weight. Now we increase the load by 1 kg and its length has elongated. Okay, then now what we'll do is, now we will remove the load, but what we'll see here is the length will not change. It will not lose its elongation. It will not regain its original size. That means beyond the limit, this body cannot regain its original size and shape. That means from 9 till 9 kg, it could regain its original shape and size when the deforming force was removed. But when we increase the load by 1 kg, what we saw is when we removed the deforming force, it could not regain its original size and shape. That means now at this load that we have applied, till this load only it can regain its shape. That means at this load, the stress that is produced in the body, it is the maximum limit of the stress within which the body can regain its original length when we remove the deforming force. That maximum stress within which it can regain its original size and shape is called elastic limit. This maximum stress produced in the body is called elastic limit. So let's define it. What it is? It is what? It is the maximum stress within which the body regains its original size and shape after the removal of deforming force. And if we go on increasing the load, then it will not regain its original size and shape. Okay, clear? So we have considered what elastic limit is. Now let's go to the Hooke's law. Okay, the statement says within the elastic limit, the stress is directly proportional to the strain. Let's try to understand it. Here, how is strain produced? To produce the strain, what is strain? Change in length by original length. That means to produce strain, we have to apply load. Okay, suppose 1 kg. That means now, because of this load, there is elongation. That means there is increase in length and strain is produced. How much amount of strain is produced? The strain produced is delta L by L. So here, when strain is produced, what happens? It is getting deformed. When a body gets deformed, what happens? There is some internal force acting on the body which tries to maintain its original shape and size. That restoring force by area is nothing but stress. That means when strain is produced by applying load to the body, what is generated inside the body? Stress. That is restoring force by area. That means what is the result here? Stress is the result of strain. And what amount of stress is produced? It depends on the amount of strain produced. The more the body is elongated, the more stress will be generated. That means more and more stress will be produced inside the body. That means what we see here, the stress produced in the body as a result of strain, it is directly proportional to the strain in the body. So this is Hooke's law, but this law is valid only within the elastic limit. That means the limit up to which the body can regain its original size and shape after the removal of the deforming force. Okay, so if we plot this, the result is strain. We always plot it, the result along y-axis and strain along x-axis. It is directly proportional, means it will be, the graph will be a straight line passing through the origin. Clear? Now let's move to the next slide. Now, from the law, what we obtain is stress is directly proportional to strain. That means when we remove the proportionality sign, we'll get a constant into strain. Then when we bring the strain to the left hand side, what we'll obtain is stress by strain is a constant. Constant means which does not change with time. Okay, but what kind of constant? This constant is same for a given material of the body. That means if we take any ball of copper or a rod of copper or a box of copper, in all these cases material is same. In all these cases the ratio of stress and strain will be constant. That means this constant of proportionality depends on the material of the body, and it is called modulus of elasticity. Modulus of elasticity, and its another name is coefficient of elasticity of the material, because it depends on the material of the body. Now again it depends on what? Now if we take this rod, what kind of strain is produced in this case? Increase in length by original length. That means longitudinal strain. Longitudinal strain. Now if we take this box, the strain produced will be change in volume by original volume. That means volumetric strain. And third type of strain is shear strain that we have discussed before. That means the type of strains produced in the given materials are of three types, that is longitudinal strain, volumetric strain and shear strain. So what we see here is this constant even depends on the type of the strain produced in the body. That means this modulus of elasticity is of three types depending on the type of the strain produced. Okay, now first type of modulus of elasticity is called Young's modulus. Okay, so Young's modulus comes when there is longitudinal strain produced in the body. That means the ratio of what? Longitudinal stress by longitudinal strain produced in the body is called Young's modulus. We represent Young's modulus by capital letter Y. Okay, and what will be its definition? It is what? Within the elastic limit. This comes because here this constant comes from Hooke's law. Hooke's law is valid only within elastic limit. So within the elastic limit, the ratio of longitudinal stress to the longitudinal strain is called Young's modulus of the material of the body. Let's try to picturize it. Here in the rod of length L, we are applying some load, because of which longitudinal strain is produced. And longitudinal strain is how much? Longitudinal strain is equals to delta L by L. When there is strain produced in the body, there is internal restoring force produced inside the body. Suppose this area of cross section is A. This restoring force divided by area is nothing but longitudinal stress. So the expression of longitudinal stress is what? Restoring force by area of cross section. And we have already discussed how can we measure the restoring force. This restoring force is equal and opposite to the deforming force. Here in this case, suppose we are applying the force of F. So deforming force is F, which is equals to restoring force. So here longitudinal stress is nothing but force by area. Okay, so let's apply this to expressions in this expression of Young's modulus, that is Y is equals to longitudinal stress, that is F by A, by longitudinal strain, that is delta L by L. Okay, so this is the expression. If we just simplify it, F by A into L by delta L, that is FL by A into delta L. This is the expression of Young's modulus. Okay, now what is the unit of Young's modulus? See, it is the ratio of stress and strain. Strain is the ratio of two lengths equal same physical quantity. It does not have any unit. That means unit of Young's modulus is same as the unit of stress. That means F by A. So what is the unit of stress? Newton per meter square. Okay, and what will be its dimensional formula? Again, its dimensional formula is same as the dimensional formula of stress. Okay, that is force by area, that is force is what? Mass into acceleration, ml t to the power minus 2 by area, that is L square. So dimensional formula in this case is L to the power 1 minus 2, that is minus 1 t to the power minus 2. Am I clear till here? So we have discussed what Young's modulus of elasticity is. Now we'll go to the second type of modulus of elasticity, that is bulk modulus of elasticity. So here first type of strain was longitudinal strain. Now second type of strain will be volumetric strain. That means we'll take a cubical box. Okay, now we will apply equal pressure or on all the surfaces, on all the faces of the cubical box. Suppose the pressure that we are applying to decrease its volume is P, which is same in all the direction on the surface of the box. Okay, and we are applying it in the perpendicular direction. So here the pressure that we are applying it is what? It is normal pressure. Okay, that is force by area. And we have discussed the force applied is equals to the restoring force developed. That means normal stress will be equal to the applied force by area, that is equals to the pressure that we have applied from outside. Okay, and now in this case, what will be the expression of volumetric strain that we have discussed before? Volumetric strain is the change in volume. Suppose the volume has decreased by amount delta V, its initial volume is V, then volumetric strain is delta V by V. So here bulk modulus of elasticity, which we represent it by K, it is what? It is the ratio of normal stress by volumetric strain. Okay, again this constant comes from Hooke's law, which is valid only within elastic limits. So what is the definition of bulk modulus of elasticity here? Within the elastic limit, the ratio of normal stress to the volumetric strain is called bulk modulus of material of the wire. Am I clear? So now let's see the expression. K is equals to what? The ratio of normal stress by volumetric strain. Let's put the value. Normal stress is what? P by volumetric strain is what? Delta V by V. Okay, now you see, when we are applying pressure, pressure is positive value. We are increasing the pressure. Volume is decreasing. One is increasing, other is decreasing. So we have here negative sign, which is showing what? We are increasing the pressure, because of which volume is decreasing. Okay, so this is the expression of bulk modulus of elasticity. Same as before, unit of bulk modulus will be same as the unit of the normal stress, because strain is the ratio of same physical quantity. It has no unit, so its unit is Newton per meter square, or Pascal. Unit of pressure is Pascal, and dimensional formula is same as before, ml to the power minus 1 t to the power minus 2. Okay, so this is the second type of modulus of elasticity, that is shear modulus of elasticity. Okay, so again, third type of strain that we had discussed before was shear strain. So you all can see here, shear modulus, its another name is modulus of rigidity. Its definition is again within the elastic limit. Okay, the ratio of tangential stress to the shear strain is called shear modulus of material of the wire. Again, first we'll see the two-dimensional figure that we have discussed before. This face is fixed. We are applying the force tangentially to the surface, because of which this face, which is perpendicular to the fixed face, gets turned by some angle. That angle by which it gets turned is called shear strain. Suppose this length is delta L and this length is L. Then we had discussed before, theta is what? Shear strain is what? Delta L by L. And we are applying tangential force on the upper surface. Suppose the area of this upper surface is A, then tangential stress is what? Force by area. Therefore, shear modulus of elasticity or modulus of rigidity, which we represented by Greek letter eta, it is what? Ratio of tangential stress with shear strain, that is theta. Now let's put the value of both. Tangential stress is force by area, shear strain is delta L by L. So if we simplify it, what we'll get? F by A into L by delta L. This is the expression of modulus of rigidity. Same as before, its unit will be what? Newton per meter square. And I leave this work to you. What is the dimensional formula of modulus of rigidity? Please do that. Okay, am I clear till here? So we discussed what? First, Hooke's law, that is within elastic limit, the stress which is generated, inside the body, that is force by area, restoring force by area. It is directly proportional to the strain produced in the body, and the ratio of stress by strain is called modulus of elasticity, which is of three types depending on the type of strains, and they are Young's modulus of elasticity, bulk modulus of elasticity, and shear modulus of elasticity. Okay, now we will discuss stress strain curve. Okay, previously we discussed the stress strain curve only within the elastic limit. That means it is directly proportional, which is a straight line passing through the origin. Now we'll discuss what will happen if we increase the load, if we increase the force applied beyond the limit, elastic limit, that is the beyond the maximum stress produced in the body. Okay, now see here, at first we see in this curve the region OA. Let's change the color. Okay. Now, here we see the region OA, which is a straight line. So in this case, what we see is at this point, the stress produced in the body is this amount and the strain produced is this amount. Okay. Now, if we decrease the stress, okay, if we decrease the stress, what we see is, let's consider diagram only. Stress is upward restoring force. Strain is elongation in the body by original length. Now, if we decrease the stress, okay, suppose we decrease it by this amount, what we see is the strain produced in the body will decrease, and we will see that if we continue decreasing the stress in the body, then strain will go on decreasing and it will follow this curve A to O, and what we'll see is when the stress produced in the body is 0, that means when the load applied is 0, then the strain produced will be 0. It will regain its original length. There is no deformation left in the body. Okay. Now, if we increase the stress in the body here beyond A, what we see is if we increase, even if we increase the stress by small amount, strain increases by large amount. Okay. So here it is not directly proportional, but here you will see that if again we decrease the stress, what we will see is it will regain the strain produced in the body will become 0 and it will follow this path BA0. Okay, and when we bring the stress to be 0, strain also becomes 0. Okay, so here B is what? Elastic limit. It is the maximum stress within which the body can regain its original shape and size when the deforming force becomes 0. Okay, now what we will do is we will increase the stress beyond the elastic limit. What we'll see is now as if the body is continuously flowing, its length is increasing, more and more strain will be produced in the body even if the stress applied, that is the force applied in the body, is very small. So this region is called plastic region of expansion. This is called plastic region of expansion. Okay, and what we will see is if in this region, suppose it has reached this point, that is P here. Okay, now we will continue decreasing the stress. Suppose we decrease the stress to the point C. What we will see is now if we continue decreasing the stress, what we will see is it will follow this path, and when the stress becomes 0, the strain will not be 0. That means the body will get permanently deformed here, and there is some amount of strain produced in the body even if the load applied to the body is 0. We completely remove the load. Okay, so here it is permanently set. The term used for this is the body is permanently set. That means in the plastic region of expansion, if we decrease the stress, even if the stress becomes 0, some amount of strain is left behind in the body and the body is said to have permanently set. Okay, and now is this curve same for all types of body? Here, if this region B to D is large, that means if plastic region of expansion is large, the materials are called ductile materials. Now, if this region is small, that means B to D is very small. if the plastic region of expansion is very small, then the materials are called brittle materials. Now let's see what is the difference between these two. Okay, so here if we increase the stress and it reaches to the point D, okay, now this is the maximum stress that can be applied to the body. Now what we were discussing, if we apply the stress to the limit D, which is the maximum stress that can be applied, which is called breaking stress. Breaking stress. Now why it is called breaking stress? Suppose the breaking stress comes when the load applied is 10 kg. Okay, if we apply the load of 10 kg, then suppose this is the amount of elongation produced in the body. Now if we remove the load and the load becomes 9 kg, even if we decrease the load, what we see is now its strain, the strain produced in the body will not decrease, it will go on increasing, and it will reach the point where it will break, it will get fractured, and it will reach to the point E, which is called fracture point. That means if we reach the breaking stress point and even if we decrease the load, it will definitely break and it will get fractured at the point E. Okay, so here what we see is in the ductile material, this fracture point and the breaking stress, it will come at a very later stage. That means we can large amount of strain can be produced in this kind of body, ductile material. Okay, so the example of the ductile materials are aluminium, copper, gold, silver, and so on. And in brittle materials, the breaking stress point and the fracture point appears at the very earliest stage. That means we cannot increase the strain by large amount. If we increase the stress, what we will see is the body will break. Okay, and this kind of materials are called brittle materials. The example of brittle materials are glass and ceramics and so on. Okay, I hope you all are clear. Now let's move to the last topic of this chapter, that is elastic potential energy of a stretched wire. Okay, now from where does the potential energy comes in the stretched wire? Let's try to understand it. Stretched wire means to a wire of length L. Suppose we are taking the wire of length L, we are applying a force of deforming force F, suppose. Okay, then its length will increase, it is getting stretched. Suppose its length has increased by delta L, dl or delta L. Okay, this is the stretched wire. Now what is the property of elasticity? When the body gets deformed, some restoring force will be produced in the body. Internal restoring force will be produced in the body, which will oppose this change in size and shape of the body. That means now if we try to increase its length, if we try to stretch it, we have to do some work against this restoring force, internal force produced in the body. That means when we do some work on the body, some energy is stored in the body as potential energy. Okay, so that is the source of the elastic potential energy of the stretched wire. Okay, so now let's try to find out what is the amount of this elastic potential energy stored in the body. To find out the amount of elastic potential energy, we have to first find out what is the amount of work done, the work that we are doing against this restoring force to increase its length, to stretch this wire. Okay, so let's consider here. Let F force is applied on this wire of length L. It increases its length by dl. Initially, when we are applying this force, when there is no elongation, restoring force is 0. Initially, there is no restoring force produced in the body when the elongation is 0. And when the length is increased slowly by applying force F, when the length increases slowly by dl or delta L, the restoring force increases from 0 to F. So what we see here is, when initially elongation was 0, force was also 0. Internal force generated inside the body was also 0. And when the length increased by dl, the force produced inside the body, that means internal restoring force, became F. So now we have to take the average of this two, that means the average of the restoring forces produced inside the body, that is sum of initial and final by 2. So the average force is F by 2. Now what is the formula of work done? Now we want to find out the work done against, we are doing work against this restoring force. Now let's recall what is the formula of work done. Work done is force into displacement. So here, what is force that we are applying? That means here, because of applied force, there is restoring force produced in the body. We are doing work against this restoring force. So we have to take the average of this restoring force produced in the body into the displacement. And here displacement is what? The elongation. That is, it is getting elongated by length dl. Okay, so here what is the average force? F by 2 into dl. Okay, so here this is the expression of the work done, that is half into F into dl. Now let's try to write this in terms of stress and strain. So what is stress? Stress is F by A. And what is strain? Strain is increase in length by original length, right? Okay, so here we must have F by A. So we divide it by F. When we divide by A, we have to multiply by A. We have stress here. Then again we need dl by L, so we divide it by L. When we divide by L, we must also multiply by L. So we get here, if we write it here, half into what is F by A, that is stress, into what is dl by L, that is strain. And what is A into L? A is what? Area of cross section. L is the length, that means A into L is the volume of this wire. That means the work done is nothing but half into stress into strain into volume. Okay, now if we erase this one first. Now work done is half into stress into strain into volume. Now this is the amount of work done. When we are doing work, energy is stored in the body as elastic potential energy. So the expression of elastic potential energy of the stressed wire is nothing but half into stress into strain into volume. Okay, now if we divide both sides by volume, therefore what we'll have? Potential energy by volume is equals to half into stress into strain. Half into stress into strain. Okay, am I clear? I hope you all understood and enjoyed this part. Now the last part is Poisson's ratio. Here, if we take the rod and we are producing longitudinal strain in it, okay, that means its length is increased by delta L. Original length was L. Okay, so when we increase the wire, when we elongate the wire, what happens to its diameter? It gets shrinked, right? That means diameter will get decreased. So that means if we denote this decrease in diameter by delta D, and initially suppose the diameter was capital D, that means delta D by capital D is what? The strain produced in the diameter, which is called lateral strain. Lateral strain. So what we see here is lateral strain is the effect of the longitudinal strain. That means when we elongate, when there is increase in length, there is decrease in the diameter, and we measure it by lateral strain, and we name the ratio of this lateral strain by longitudinal strain as Poisson's ratio. Okay, and this ratio is called Poisson's ratio only within elastic limit. So here the definition of Poisson's ratio is within the elastic limit, the ratio of lateral strain to longitudinal strain is called Poisson's ratio. Okay, and what should be the value of Poisson's ratio? Practically its value lies between 0 to 0.5 practically, but theoretically its value can lie between -1 to 0.5. This is very important. And last thing that I want to discuss here is one very important and interesting question: is steel more elastic than rubber? What shows that the body is more or less elastic is the amount of restoring force. By what amount it can oppose the change in the length. Okay, let's recall the ratio stress by strain. Stress by strain. Suppose longitudinal stress by longitudinal strain. This was what? Young's modulus. So suppose we consider again the rod shaped object, one made up of steel, another suppose again it is made up of rubber. When we are comparing something, okay, what we do is we'll try to take it of same length and same area of cross section, and now we'll take same amount of strain produced in the body. Okay, suppose we have increased its length by delta L. Here also the length is increased by delta L. That means strain is same for both. Okay, that means when we apply strain, what is produced inside the body? Stress. That means internal restoring force by area. Okay, now if the body opposes more to the deformation, that means more restoring force is produced. If more stress is produced, then the body is more elastic. Now see, in this cases, that is steel and rubber, in which case more amount of stress will be produced. Here we can see in steel only more amount of stress will be produced, that is restoring force by area. More amount of restoring force by area will be produced in case of steel. That means steel is more elastic than rubber. More elastic than rubber. Okay, that means for the given strain produced in the body, if more amount of stress is produced in the body, it is more elastic. That means if stress is more by strain, what will be more? Young's modulus will be more. That is, by seeing the value of Young's modulus, if Young's modulus of steel is greater than Young's modulus of rubber, that means steel is more elastic than rubber. Okay, so we have come to the end of this chapter. I hope you all have understood it. Okay, in the next video we'll be discussing some numericals on this chapter. Please like and subscribe if you like the video. Thank you.